Okay, everybody, today we have a problem with comparable instructions to a competition problem. Now, non-void means the same thing as non-empty or not equal to this vacuous set. And of course, the empty set just means this, and we're all familiar with this. In a way, to me, it doesn't seem like this should be even mentioned, because an empty set doesn't have any integers in it, so it seems like it's superfluous to even say that. But in any event, this is more or less how the instructions were in the competition. Now, cardinality, we mean size. Okay. Cardinality and size are synonyms. As far as I know, I've seen some people fight about that philosophically, I guess. But let's talk about an example here. Notice that the cardinality of S here is certainly you use the absolute value bars to connote cardinality, and so you can call it the absolute value of S, but it just means the set size. And there's certainly 3 elements in there. Okay, so that's equal to 3. And you could have made this, the set of directions include this type of terse notation. I think a lot of times in competition problems they like to use more language, than symbology. But in any event, an example of such a set is this set right here, since 3 is certainly the least element, right? And then there's 2 extra elements in there for a cardinality of 3. Now, let's get busy systematically. How would you handle this problem as far as counting all of them, all right, with this property? In this very first case is quite simple. There's only one such set of size 1, and that would be the element 1. All right, notice that if you picked a bigger element, it would, like, for example, you couldn't have 2 because you would have to have 2 elements in that set, right? Okay, now in a similar fashion down here for size 2, you have to exclude 1 as being in the set, all right, since 2 is the least element. And also there's 7 choices from 3 to 9, right? From 3 to 9 inclusive is an additional 7 choices. For example, an example would be 6, right? That would be a number. This is just one of the 7 examples, right? Okay. So hopefully this notation means something. I just kind of made it up on the fly. Now right here for 3, we're having to exclude 1 and 2, right? You can't have 1 and 2 members of this set, obviously, because that would make 1 or 2 the least element, right? But that squeezes down the number of possible choices other than 3, the numbers between 4 and 9. But there are 6 of those, and we need 2 of them. That's why we have to use this 6 choose 2 notation. Okay? Y'all, it's the very same kind of reasoning all the way through. Now, at the very end here, it's very clear that the only 5 elements that would qualify would be 5, 6, 7, 8, and 9. And so I listed, just like I physically listed it. We could have called this 4 choose 4 if you feel like it, but it's kind of overkill on the notation. That's the same as 4 choose 4, but n choose n is always 1, right? But in any event, you can just physically enumerate it. Here you can't. It's a hassle to actually list all of these possibilities, so you have to list it generically, sort of, and then use this combination formula, okay? So notice, folks, the count here is pretty easy to do here. I see 1 plus 7 plus 1 here, that's 9. And then we have plus 15 for the 3 case. And then plus 10. And y'all, that looks like it adds up to 34. So that's the solution to this problem, folks. Now, y'all, if you wanted to turn this into a probability question, you want to say, what is the probability of randomly picking a set with this property? That's an easy one to write down. We can write down probability would be, and here's where the void set actually means something. The probability of an event like this would be the favorable outcomes, which is 34 in this case. But we're not interested in the void set. Okay, now remember there's 9 elements in the set, right? There's 9 elements to choose from. And so you would have to subtract off 1 from that. So that would be 2 to the 9th minus 1, right? Because the binary form 9 zeros would correspond to the empty set. So 34 divided by 2 to the 9th minus 1 would be the probability of something like this occurring. Now, and again, we're done. This finishes what we were set out to do. I just wanted to point out, though, that this example set would have occurred as one of the 15 forms down here, right? This 537 would be one of the, you can write a set in any order. I wrote it in the order I wrote it in, just it's cleaner to look at it that way. But this is one of the 14, this is one of the 15 three-element sets that enjoys the original problem statement. So answer is 34. I'll write it again up here. Thank you for viewing.